All right, welcome to part two. Chapter 2, acids and bases. Let's pick up where we left off. We did an introduction of acids and bases, talked about the the first definition of acids and bases was based on Arrhenius, H plus, OH minus, not very practical. Bronsted, Lowry came along and further developed this this definition. So it's proton donation. An acid's a proton donor. A base is a proton acceptor. All right. So we talked about pKa and what that means and where it comes from mathematically. And we're now in 2.4. Okay. This is predicting the outcome. So the question, I said everything is in principle in equilibrium, but the question is, how do we know which way that equilibrium lies? Which one's a stronger acid? Which one's a stronger base? Okay. Basic rule, strong reacts with strong. They're going to be on the same side. Okay. The strong acid and the strong base are going to be on the same side. They're going to interact. Things want to get to a lower, a more stable point. Okay. Thermodynamics. We'll talk about that later in some other cases, but there's equilibrium, but there's sort of a desire for the reaction to get to the weaker species, the more stable species. I want you to think synonymously, weak equals more stable. Stronger acid reacts with stronger base to form weaker acid and weaker base. Okay, so if strong reacts with strong, weak does not react with weak. Okay, so let's look at some examples. It's a really interesting one, and what I do a lot of times in this course is I sort of foreshadow. That's a CC triple bond there. It's just a carbon that I've tried to fix up a little bit. CC triple bond. This CH is a special kind of CH. We'll get into this called the hybridization effect. Okay, we'll come back to this stuff. We'll see stuff repeated throughout the course in deeper ways. Okay, well, let's look at this CH bond with two different bases. We're looking at two different equilibrium reactions. This K plus NH2 minus, and same starting material. This is acetylene with a K plus O minus. Let's just make it OH minus. So we want to predict, and this is the power of all the things we're learning. It's going to help you predict things. How do we know one of these bases will deprotonate this H and one of them will not? We're going to get into what's called the element effect shortly. Okay, right now we're kind of looking big picture stuff. One of these is stronger than the other. One of these bases here, I'm going to circle the two bases in these two reactions. One is stronger than the other. Okay. So again, in principle, equilibrium. So let's draw the products. If each of these bases deprotonated acetylene, you'd get an anion with a K plus. You get the same product. And you get, from these bases, you get protonation. In this case, you get ammonia up top and water. Everything's accounted for. You got a minus and a plus on the left side. You got a minus and plus on the right side, etc. Okay, so charge, the charges are maintained overall. So if I tell you that this one will deprotonate, the equilibrium lies to the right. That's what these uneven equilibrium arrows mean. We're making a prediction that these are favored. Whereas in this case, these starting materials are favored as we've drawn it, or the products if you went right to left. Okay? So the big question is why? Well, right now, let's look at pKa equals 25. We'll learn why in a deeper way. But right now, pKa 25. And what you're doing is looking at the acid on one side. There's an acid, and there's an acid. pKa of 15.7, pKa of 38 for ammonia. So we're comparing. We have 25 versus 38. and 25 versus 15.7. The rule is pKa, lower pKa, stronger acid. So when we compare 25 to 38, this is the stronger acid, 10 to the 13th times stronger, I might add, which is very significant. So that means that this base is the strong base, and this is the strong acid. The strong is reacting with the strong. So those two interact, and they give the right side, the products on the right. However, when we look here, 25 versus 15.7, which one's the better acid? Water is the better acid. So this is the strong acid, and this is the strong base in this case. Again, it's relative. Up here, notice the acetylide anion right here was the weak base. Now it's the strong base. It's all relative. Water is a stronger acid. This is the weaker base down here, and this is the weaker acid. Okay, so that's what we're going to look at next is why. We want to understand atoms and how they interact, and that is 2.5. So section 2.5, if I had to give the most important section in this book, it's this one. Okay? 2.5, the most important section in the textbook. Factors that determine acid strength. Factors that determine acid strength. Okay, so let's look generally. HA, we've been using this sort of general idea. We're going to look at 4 factors. Okay, these are sections 2.5A, B, C, and D. So 2.5A is the element effect. Element or electronegativity effect. Okay, we'll look at kind of 2 of these, 2.5A, sub point 1 and 2, but it's the element effect, the atom in question. Okay, these all make more sense. 2.5B is called the inductive effect. 2.5C is called the resonance effect. 2.5D is called the hybridization effect. Okay, if I had to pick 2 of these that are the most important, it'd be 2.5A and 2.5C, element and resonance. Okay, inductive is very important, and so is hybridization. Okay, 4 effects, extremely important. Okay, so what I want you to do is when you look at an acid, okay, well, let me give you some rules here. Rules or guidelines. Stabilization, when we talk about the strength of an acid, HA, the stabilization of a minus, that's the conjugate base. The more stabilized A minus is, stronger acid HA. Okay. More stabilized A minus is, stronger HA acidity is. Weaker A minus is, stronger HA. So stabilization makes something weaker. The more stabilized it is, the weaker it is. Okay, so there's these 4 different effects. What I want you to do when you look at an acid is, so question is acid strength. So you're looking at an acid, HA, right? I want you to draw the conjugate base. And when you're comparing 2 different conjugate base, you're going to determine which one's more stable between the 2, if there's or 3 or 4. Okay, you're going to compare. If you have 4 acids, you're going to compare 4 conjugate bases, and you're going to decide which one's the most stable, which one's the weakest, and then you're going to determine which is the strongest acid. So you have to look at the base. Okay, you can do this by looking at the acid as kind of we'll talk about this a little bit more in class. There's kind of another side of the coin. But I'm gonna teach it as you're gonna look at the bases, okay, and extrapolate back to the acids. So let's look at element effect number 1. 2.5a is the element effect. Let's look at the periodic table. It's also, I might call it the electronegativity effect. It has to do with the electronegativity of the atom in question. Now, we established this in chapter 1. We talked about electronegativity. We talked about dipoles that result from electronegativity. The trend on the periodic table is up and to the right, okay, for electronegativity. So the first one follows that trend just fine. We're going to go from left to right. So we're going to look at 4 different acids and their conjugate bases. So here's a test question. I'm going to give you 4, and I'm going to draw them in the tetrahedral sp3 hybridized fashion. So there's methane, CH4. Here's ammonia. I just want to reinforce what we've talked about. That pair of electrons is held in an sp3 orbital. There's water. And finally, HF. A little harder to draw, but just to drive home the point that HF fluoride, the fluorine is sp3 hybridized. So let's look at pKa's. 50, like we mentioned, 38. We've mentioned all 4 of these, or 3 of these. And actually, HF is not nearly as acidic as HCl. And that's a bit of an oddball, and we'll, not as much of a focus, but we'll mention that in a second. 50, 38, 15.7, 3.2. Still the best acid. So we have 4 here. You're not going to be given the pKa. So I'm going to ask you, which of these is the strongest acid? Or better yet, rank them. And they will be in this nice order. Rank them 1 through 4. Strongest acid being 1, weakest being 4. Okay. I could give you pKa tables and you could learn how to use them, but you need to learn the trends. It's going to benefit you in the rest of the course. So we're going to draw the conjugate bases. Remember the route that I told you to do this was draw the conjugate bases. So deprotonate, again, some imaginary base is going to rip off 1 proton. In the case of HF, there is only 1 proton. So now you have 4 conjugate bases. Okay, so we see increasing acidity up here. Question is why? Well, we can use electronegativity to understand this. Which of these atoms is the most electronegative? It's fluorine. Let's rank the electronegativity. 1, 2, 3, 4. The atom with the anion, we're looking at electronegativity. Why is electronegativity important? Because electronegativity is an affinity for electrons. Fluorine has 7 electrons in its valence shell. It very much wants another electron. So never mind the fact that that has a minus charge. Look at the octet. It is full. All the octets are full, but fluoride, more than any other, wants to fill its octet. Okay? Think of if you personified these elements and you looked at the periodic table, you'd say fluorine, chlorine, bromine, and iodine are electron bullies. They are going to beat up other elements to get that extra electron more than anybody else. Oxygen wants 1 too. Oxygen wants 2, actually. Nitrogen wants 3. Carbon wants 4 from its valence. But fluorine wants it more than others. Okay? So the most electronegative atom means that the negative charge, the fluorine is the happiest to have a negative charge. Why? Because it has an electron affinity, wants to fill its octet more than the others. Okay, it's so close, it wants to get to that neon noble gas configuration. Okay, so what do we have? We have increased electronegativity. which leads to increased stability. Okay? Increased electronegativity, increased stability. Fluorine is the most stable atom with a negative charge of these four. Okay? So if fluorine's the most stable, the weakest, which one is the least weakest? Okay, the strongest is over here. It's the opposite trend. So strongest base, because it's the least electronegative, weakest base. Weakest base correlates to strongest acid. Okay, you need to be able to do this analysis. Weakest acid. Okay. All right, very, very important effect. All right, let's also look at let's go down the periodic table, and this is going to be slightly counterintuitive. Okay, we're going to look at F minus as well. Okay, so let's look at HF, HCl, HCl, HBr, and HI. Now the trend actually is most acidic down here. Okay, this is not that big a deal. I want you to treat these all as strong acids. HF is the outlier, but this is -7, HBr is -9, and HI is -10. So HI is super strong acid. Okay, so let's draw our conjugate bases. All the lone pairs, Br minus, I minus, and our rationale for this is the size increases. So the size outweighs the electronegativity. Okay, so even though fluorine is the most electronegative, I is much, much bigger. Okay, so the size leads to increased polarizability. Okay, larger anion, that negative charge is spread out over a larger space. This is a good introduction to a term called delocalization. Okay, when something's localized, it's in one spot. When it's delocalized, it's spread out over a bigger area. Okay, so I minus. The iodine's the biggest one. That minus charge is spread out over a much bigger area rather than the tiny fluoride ion. Okay, so if you look at, qualitatively, bigger. Okay, so this is very important. Okay, I do want you to understand this. We call it polarizability. Okay, so it doesn't follow the trend of electronegativity. It follows the trend of size. So size increases down the table, and polarizability increases. And HF is the outlier because it's only 3.2. And the reason is because fluoride is a similar size as an H. There's hydrogen bonding. Okay, so actually HF can hydrogen bond with itself. That decreases the acidity. That's the argument. Okay, so that point is not nearly as important as understanding the polarizability. Okay, so larger atom, negative is spread out over a larger area. Okay. All right, let's look at inductive effects. Okay. Inductive effects are also based on electronegativity, but it's a removed atom or set of atoms. Okay? So number 2 is inductive effects. This is the fact that electronegative atoms stabilize nearby charge. Again, you can look through the book at these things. Electronegative atoms stabilize a nearby charge. Okay, so the element effect, we looked at 4 different atoms carrying a negative charge. Here we're going to have the same atom, oxygen, for example, carrying a negative charge, but we're going to have other atoms attached. Okay, and it's a pull of electron density through sigma bonds. We're going to be using all this terminology from chapter 1, so you got to get that down. Sigma bonds are single bonds. Okay, think of them as conduits of electron density. Electrons, they're not moving through there. The electron density can kind of fluctuate. If you look at electrostatic potential plots, figure 2.2, it gives a nice color picture of what I'm about to describe. And I'll come back to that in a second. Pole of electron density through sigma bonds. Let's look at two molecules, ethanol, CH3CH2OH, and trifluoroethanol, CF3CH2OH. The pK of this is 12.4, and the pK of here is 16. So trifluoroethanol is a better acid. Why? Let's draw out, once we deprotonate, let's draw out everything. There's our anion. That's just a stray mark there. Forget that. There's a minus charge on the oxygen. Again, we're past calculating formal charge already. Okay? So now, got an O minus and an O minus. So now it's not the element effect because the element is the same. It is electronegativity, but we call it the inductive effect. These fluorides are going to play a role. Fluorine's different than hydrogen, right? Fluorine's more electronegative than hydrogen. So what do we have? We have dipoles. This electronegative atom forms 3 dipoles, forms a net dipole that is pulling electron density away from this oxygen. So this one, here's this term again, the O minus is localized. It's all there. It can't go anywhere. It can't be shared. These fluorides, all 3 of them are pulling electron density away by this net dipole. Okay, so some of this minus charge is kind of being sucked out through the sigma bonds into the fluorides, so to speak. Okay, that's what we mean by a through sigma bond effect. That sigma bond is acting as a conduit of some electron density. It's just being pulled out. If you look at the electrostatic potential plot, figure 2.2 on page 73, you see the red O minus is much bigger on the ethanol derived rather than the trifluoroethanol. So the one on the right is spread out, that negative charge is spread out over a larger area, similar to the I minus. The bigger atom spreads it out. The bigger group of atoms, not bigger, but the more electronegative atoms, the trifluoro group, spreads out the negative charge. Okay, this is seen in other cases too. There's plenty of cases. You can work some of the problems and look in your solutions guide. Let's move on to resonance. Okay, we'll see so many resonance forms. You'll be seeing resonance arrows in your sleep. So now we're going to look at ethanol again. We said pK of 16, and we're going to look at acetic acid, pK of 5. So pK of 5 is lower. That's easy. You can look at a number. You guys know that 5 is less than 16. That's not what we're testing here. Okay, we're testing whether or not you can understand the concepts here. Why is 5 lower than 16? Why is acetic acid a better acid than ethanol? Same concept. Draw the conjugate bases. Okay, we've deprotonated with some imaginary base. We've drawn an anion. We established already that there's no inductive stabilization that O minus on the left. Okay, it's localized. We've already, now there's different kinds of localization. There's polarizability delocalization, there's inductive delocalization, and there's resonance delocalization. And the same is true for localization. That O minus can't go anywhere. It's localized. What is the big difference here? We've drawn this resonance structure. Let's draw it again. This arrow can push in. These can come up. Those electrons go up. And what do we have? We have resonance delocalization, resonance stabilization. The more resonance forms you can draw, the more delocalized, the weaker, the more stable. You could draw a hybrid of this. Right? It is shared. Weaker conjugate base, stronger acid. Stronger, more localized conjugate base, weaker acid. Okay, so weaker, stronger. Why? Weaker because of resonance. Stronger because of localization, lack of resonance. Okay, lots and lots of examples of this that you can work through in the book. Let me give you a take-home example for this. CH3, propane is that. Okay, we're actually going to deprotonate here, so let me put the H's in there. Just expanded the CH3. And then acetone, common organic solvent that you'll use in the lab. Okay, we're comparing the acidity of these two H's. pKa of 19, pKa of 50. 10 to the 31st times more acidic is acetone than propane. Why? 19 is lower than 50, obviously. Why is it 19 and 50? Well, let's draw the anion, the conjugate base. This anion is localized, cannot go anywhere. Remember what a resonance structure is. It's only movement of electrons. You can't push that in there and kick out an H or anything. However, I was going to make this take home, but that's all right. I'll do part of it for you. The C is implied there. You'll see that a lot. There's the minus charge. Draw a resonance form. I want you to draw that resonance form. Okay. This is resonance stabilized. The one on the left is localized. Very, very important concept here. All right. Hybridization, number 4. Also a very important concept. Hybridization in general from chapter 1 is very important. Okay. The hybridization effect in terms of acids and bases is less important, but still very important. This is hybridization, and we're going to say this is essentially a carbon phenomenon. It's not only that, but we're only going to worry about carbon. So let's look at 3 atoms. I'm sorry, 3 molecules here. We're going to look the same 3 that we looked at when we developed this hybridization model, sp3, sp2, sp. Okay? We have ethane, ethylene, and acetylene. We're going to look at these 3 atoms. Keep saying atoms. These 3 molecules. Okay? So we got 3 pKa's. 25 is less than 44 is less than 50. You see a drastic difference between sp and sp2. Okay? Not as much between sp2 and sp3, although you do see a difference. So we have increasing acidity, increasing acidity. This is the strongest. So why? Let's draw it out. When in doubt, draw everything out. So by definition, this has to be the weakest. Again, why? We want to understand why. Well, let's look at this. We said these are sp3, sp2, and sp. Okay, this must, and we kind of talk about sp1 if you want to kind of think about that. One of the s and one of the p mixed. So clearly, it's a result of hybridization. What do we mean by that? Well, we talk about something called percent S character. The percent S character. sp3 has 25% S. sp2, 33% S, 50%. Huge difference. It's actually pretty close to the pKa numbers we see. You see a pKa unit difference of 6 from sp3 to sp2, and you have an 8% difference. But then you go 17% difference, and you get a 19% pKa, or 19 pKa unit change. And so the more S character, the more stable, or the weaker, an anion. Why is that? Well, the way we rationalize it is that an s orbital is closer to the nucleus. It's a lower energy orbital. It's closer to the nucleus. So that means the negative charge is held closer to the nucleus. Therefore, it's more stabilized. Okay? So the negative charge is pulled closer to the nucleus. It's less out there. Okay? It's less out there doing damage. Okay? So it's a weaker base weakest, therefore strongest. Practical implication, we can deprotonate this H with some reasonable bases, make a carbanion, and do some really cool chemistry. We'll see that much later, okay? Hybridization effect, very, very important, okay? All right, so those 4 effects, again, like I said, possibly the most important section in this book is section 2.5. Section 2.6 is simply some common acids and bases. Again, if you were to skip over 2.5 and go straight to 2.6, you would just be memorizing, okay? I could give you a pKa table and you could say, oh, 4.8 is less than -7. Great, big deal. All that is you're able to know that a number is smaller than another number. That's not the point. So 2.5 is tremendously important, okay? So I'm going to mention this again. I want you to get this HCl, H2SO4. Let's lump these together, HBr, HI. You'll see these 3 a lot. You'll see HF a whole lot less. Those 3 are all very strong acids. H2SO4, very strong acid. Another one that is just like sulfuric acid, we should draw out the Lewis structure of sulfuric acid. This is an interesting one because it's para-toluene sulfonic acid. Okay? This is also pKa -7. Okay, so 5 acids I want you to memorize that are only strong acids. Okay, and very strong acids, whereas acetic acid is not nearly as strong, but much stronger than ethanol. Okay, so really got to get this stuff down. These 2, vinegar on the left, acetic acid, much stronger than ethanol because of the resonance effect. Okay, this is much stronger than acetic acid. Let's draw a triangle that way. These 2, especially the toluene sulfonic acid, we call this PTSA. Okay, you'll see that again later in the course. Sulfuric acid, very strong acids. Why? Because they have an extra resonance form. So you should deprotonate this, draw the conjugate base of, and see how there's 1, 2, 3 oxygens. Draw the resonance forms of those. Okay, do the same thing for sulfuric acid. Understand why PTSA and sulfuric acid are better acids than acetic acid, and understand why acetic acid is a better acid than ethanol. Okay, it's all resonance. HCl, HBr, HI, that's more of the element effect. Cl, Bri are electronegative atoms, and so therefore they're happier with a negative charge. Okay, so very strong acids up here, medium right here, weak. Okay, so a little bit of a review of those concepts. Bases, there's a whole bunch of bases. A lot of these are listed in the book. Okay, we'll see them as we do reactions. Again, to give you some guidelines, we'll see this base at some point. This is called N-butyl lithium. Okay? It is a carbanion. It's the strongest base you'll ever see. All right, we said that this alkene, butane, we'll get to that in chapter 3, weakest base you'll ever see. Okay, very strong base, very weak acid. The opposite end of the spectrum, I minus, is the weakest base you'll ever see. Not necessarily the weakest, but one of them. HI is one of the strongest acids you'll ever see. Okay, so I minus, Br minus, Cl minus, even F minus. We are never going to use those to pick up protons. They're all weak bases, along with the negative from the sulfonate. Okay, technically that H actually has some level of acidity. We won't go into that nearly as much. We're going to treat that as a spectator ion. And in any event, though, that because of resonance, that is very stable. All right, so that's just kind of an overview, and I'm going to do one more lecture for this chapter on Lewis, the Lewis definition, and so we'll stop there and break it up that way.